So in this third video, it is still about this story, but I'm going to go and concentrate on a particular situation. The situation is starting here in this part of the fall, where the ball has collected up a whole bunch of kinetic energy, and then it gets squashed, crushed, but then it comes up and out of that. And earlier in the very first video, so this is now the third video in this little series, I told you that I was only considering two different types of energy, but I alluded to the fact that actually maybe when I consider the total energy of the system, that it won't just be a kinetic energy and a gravitational potential energy, but that in fact I was going to have to add another potential energy that is called elastic potential energy. I don't even know if you can read this in the pencil. I think you can. So this elastic potential energy is another form of energy that I need to consider if I really want to understand the energy story of the rubber bouncing ball. In physics, this is actually a big deal. The idea is when experimentalists or when physicists do experiments, they often actually don't know where the energy can hide. Or a better way to say this is, how can a system store or manifest its energies? And when scientists are trying to understand what are all of the ways that nature can behave, a little bit of that question is simply asking, how can nature manifest energy? Like, what are some interesting novel ways that energy can keep track of, nature can keep track of energy or hide it or store it. Yeah, so fundamental physics is, a lot of it is about how does nature hold on to and move energy around. So here is a place where energy can go and hide for a second. It hides in the deformation of the ball. So elastic potential energy is energy, and I'll put it stored in quotations, stored in deformation. So deformation is, here the ball is nice and circular, and then it gets deformed. And another way to put this is, it takes work. It takes a force over a distance to deform a ball. And this, I'm going to, in the ideal case, I'm going to say that all of the work that goes into deforming the ball can undeform and do the same amount of work on its environment. That's a funny way to say that, but this is the idea. So elastic potential energy is energy stored in deformation. So let me redraw the set of moments in time that are interesting for us now. So this is the moment in time right before, I know I'm calling it capital E, but that's the moment in time, that's not the energy. It's when the ball has fallen all the way through all of the height h. F is the situation of the ball being squashed and being at rest. G is the situation immediately afterwards, when the ball has undeformed and is now headed back up into the air. So let me add a little bit more motion there. Okay, so hopefully you can say that the energy in situation E is equal to, there's a bunch of kinetic energy plus, I'm going to describe in just a second that I'm going to remember that the gravitational potential energy when the ball is at the table's height is 0. But now I'm going to consider the fact that this has an elastic potential energy. So I'll put little e for elastic. So if I think about this, there is no gravitational potential energy. There is no deformation yet. But there is a bunch of kinetic energy, and this is going to be strange, but if you remember, the energy at B, C, D, actually all of the total energies leading up to this point have been mgh. So I know that because there was no external work between all of these different moments in time, that the energy cannot have been different from mgh. So the total energy is going to add up to mgh, which means that the unknown kinetic energy for time E is also mgh. Okay, so no big deal. It becomes more interesting though when we go into situation F. So the energy in situation F cannot be different from the energy in situation E, and the reason is because the work done was 0 between E and F. The work done by external force, there's definitely internal forces. There's an internal elastic squishing force, for example. But anyways, so the energy at situation E is not different from the energy at situation F. And because the energy at, so that's the conservation of energy statement, because there is no work being done. The energy did not change. So E sub F, though, the energy in time F, there is kinetic energy at time F, there is gravitational potential energy at time F, and there is elastic potential energy at time F. There is definitely going to be non-zero elastic potential energy at time F. Here it is. You see the ball is all squished up. It took energy to do that, so that energy is there. But this is when the ball has reached the very, very bottom, right? It's no longer moving. It's at the in-between case of heading down and heading back up. So it's neither heading down nor up. So it's at rest. And so it has no kinetic energy. It's also at the tabletop. And when the ball is at the tabletop, there is no gravitational potential energy. But what there is definitely elastic potential energy. But because the energy at time F is equal to the energy at time E, because there was no work done, then you can see that this must be the energy at time E, which is mgh. This is the total energy of the system since time B, actually. B was the time after the person in the first video did the work. So this means that the elastic potential energy stored up in the ball in situation F is mgh. So, okay. Yeah, so I'm going to do this. I think there's time. And I think it's interesting to do this. So, the total energy in situation... Actually, let me go back a moment. So, let's look at situation D. D was in the previous video. The ball was at half the height. So I'm going to do something. The situation D, let me draw it here. The ball was at h over 2 above the ground, had a little bit of motion. So D, so I'm not going to put an equal sign, this is a colon. So the kinetic energy in situation D was mgh over 2. we got this earlier, and this is a little bar graph. The gravitational potential energy in situation D was also mgh over 2, but in situation D, there was no elastic potential energy. So I'm going to put that the elastic potential energy in situation D has no value. So the bar graph is level. This is like an energy bar graph. In situation E, the kinetic energy is maximized at mgh. There is no gravitational potential energy. So I'll put a little flat bar here. It's 0. And there is no elastic potential energy at E either, because in E there is no deformation. Also 0. 0 plus 0 plus mgh is mgh total energy. 0 plus mgh over 2 plus mgh over 2 is mgh total energy. E at F, there is no kinetic energy. The kinetic energy is 0 at F. There is no gravitational potential energy because we're at the bottom. But there is a whole bunch of elastic potential energy. That's where all the energy is at this moment in time. So what we're watching is the energy change forms. It gets kind of swapped around. And the reason energy moves around internal to a system is internal force. So internal forces, internal to a system, they just move energy in amongst the parts of the system. So even though there are internal forces, these internal forces, the idea is that these internal forces cannot change the total system energy. All they can do is change which parts of the system have the energy and what form does the energy take. Is the energy elastic potential? Is the energy gravitational potential? Is the energy because there is material in the system that has motion? Kinetic energy. So internal forces do this. External forces, though, external forces are the reason why the total system energy can change. If there is no external force, if the system is isolated from the external world, then the system's energy cannot change. That's the argument. This is likely a new point of view on thinking about nature, and it's sort of like a summary of many ideas. Yeah.